Hello. In this segment, we're going to be talking about the fetch and execute cycle in the little man computer that actually implements individual instructions in a little microprogram inside the control unit within the little man computer. Let's start by addressing the von Neumann architecture again. In the von Neumann architecture, we have one path to memory from the CPU, and memory holds both data and instructions. So this one path to memory can become a bottleneck, and this is called the von Neumann bottleneck. But it's important to notice that instructions come from memory and data comes from memory. So we'll have to fetch an instruction from memory and then execute that instruction. If that instruction references an operand that's also in memory, we have to do another fetch. This is a picture of a detailed architecture of the little man computer that contains all of the various components that we would normally see. So we have timing and control in the upper right. That contains the little microcode programs to execute individual instructions. We see memory and the access to memory through the memory address register and the memory data register in the lower right. We see the arithmetic and logic unit in the center toward the bottom. We see the accumulator. We see the program counter, the increment register, the instruction register, and the decoder. All of these are individual components that will receive data and send data to one another. Control signals are generated by timing and control such that they determine the order of operations, they control access to the bus, the loading of registers, and so on. For example, here's a signal that controls whether or not the accumulator has access to the bus or not. Signals 0, 2, 7, and 12, as we'll see in a table in just a moment, control which data gets written onto the bus. And this is important because we can only have one piece of data on the bus at a time. This particular control signal selects what gets put into the program counter. Does the contents of the bus get put into the program counter, or does the contents of the increment register get put into the program counter? Here we see two control signals that select among addition, subtraction, multiplication, and division to be performed by the CPU. Since we have two control signals, we have four different possible combinations, so this arithmetic and logic unit can execute four different arithmetic instructions. Here's the table of micro instructions that are in timing and control. Each of these numbers is a control signal that corresponds to one of those boxes in the data flow diagram. For instance, number 0 allows the accumulator to flow onto the bus. From there, the contents of the bus can be shifted into a new location. Number 1 allows us to load the accumulator. Normally the accumulator is not going to be loaded. It'll just retain its contents from the previous instruction. Number 2 allows us to transfer the contents of the program counter onto the bus. Number 3 allows us to load the program counter with some new data. Number 4 allows us to load the instruction register with some new data. Number 5 allows us to load the memory address register with some new data. Number 6 allows us to send the memory data register, that is the contents of something that we've read from memory, onto the bus. Number 7 allows us to load the memory data register from the bus so that we could perform a store instruction. Number 8 allows us to transfer the contents of the ALU into the accumulator. So we've performed a read, or I beg your pardon, we've performed an add or a subtract, and we want the new result to go into the accumulator. Number 9 allows the program counter to be incremented so that the next instruction fetched will be one more than the previous instruction. Numbers 10 and 11 allow us to select among addition, subtraction, multiplication, division. Number 12 allows us to send the contents of the address portion of an instruction to the bus so that we can do a subsequent fetch on a load instruction. Numbers 13 and 14 control access to the memory. Number 13 is the chip select, which activates memory, and number 14 is the read-write bit. If it's a 1, it's a read. If it's a 0, it's a write. So using these control instructions, we can have a detailed fetch and execute cycle as a flow diagram. So each of these steps corresponds to a little program that exists in the control unit. And as a fetch and execute cycle, we should be able to break this down into those two separate operations. So the top 3 micro instructions are the fetch portion of the execution cycle, and the bottom are the execute portion. Of course, the execute portion is conditional because we don't treat a load or a store the same way as we would treat an add or a subtract. So let's flow through an example instruction being executed as a microprogram. Let's assume that this is a load instruction. So the first thing that we're going to do is we're going to try and fetch the instruction from the contents of memory. So the first thing that we do is we need to know where that instruction needs to be fetched from. So we send the program counter onto the bus, and then from there we can load the memory address register so that we can do a subsequent read from memory. But at the same time, we're going to increment the program counter and load a new value into the program counter register so that we're prepared to execute the next instruction in sequence. Then we're going to activate memory so that we can read. The instruction address is in the MAR. We turn on memory and we assert the read line, and after this is completed, we will have the next instruction to be executed in the memory data register. From here, we need to transfer that into the instruction register so that it can be decoded. So we send the MDR to the bus, and then from the bus, we load the instruction register. If we assume that the instruction is a load instruction, then the opcode will go into timing and control so that we know which portion of execution we're going to do, and the address of the load will flow back onto the bus and then loaded into the memory address register. So now we're going to fetch the operand that will be loaded into the accumulator from memory. We then assert the chip select and the read bit to activate memory, and now the operand is in the memory data register. But we need to get it into the accumulator. So we're going to send the memory data register onto the bus, and then we will load the accumulator from the bus. And now we've completed the fetch and execute cycle. The fetch and execute cycle, as we see it here, does not handle branching instructions. So how would it need to be modified so that we could handle branching? The answer is, between the fetch and the beginning of execution, we need to determine whether or not a branch is taking place. Because if a branch is taking place, we need to go back up to the top and fetch the instruction that we're going to branch to. So between these two, we will insert some conditions. If the opcode is an unconditional branch, then we're going to take the address that's in the instruction register and we're going to send it to the bus and use that to load the program counter. We've now overwritten the program counter so that the next instruction that gets executed will be the one that we've specified from the address operand of the current instruction. Otherwise, if it's not an unconditional branch, we look down to see if the operation is a branch or not. If it is a branch that's conditional, we have to check the contents of the ALU to see if it's 0 or positive. If that condition is met, then we'll do the same thing, send the address to the bus and load the program counter. Otherwise, it's not a branch instruction, it's a load or a store or an add or subtract, and we'll just flow through the rest of the instructions that we find in the microcode. In summary, the fetch and execute cycle consists of many steps and is implemented in the control unit as microcode. That's to say that every individual instruction actually has a little program that executes on the CPU in order to actually carry out that instruction. Control signals are going to select operations, they're going to control access to the bus and allow data to flow from component to component within the CPU. Adding new instructions to our instruction set means that we're going to modify the microprogram that exists in the control unit and is implemented in hardware.